Hello students, so we'll continue the video of design of gears, design of Spur gears. So next thing is we'll talk about number of teeth, the minimum number of teeth to avoid interference. Although you have studied about interference is a phenomena when we see two gears are meshing with each other like this, okay, and these two teeth, the pair of teeth, they clash with each other. That means due to let's say problem in the involute profile of their involute profile, this gear will dig into this one. I mean their profile clashes like this, okay, this in this manner. While leaving, this gear will just cut this teeth, okay, in this way, okay, like this. Then that is a type of problem. They will actually interfere with each other and they will not rotate. That is interference. Okay. So you see we have studied about three type of involute systems: 14.5 degree full depth, okay, full depth involute. That is nothing but this angle, right? I have spoken about this angle, this alpha. This is 14.5 degree. This may 14.5 and 20 degree both are there. So 20 degree full depth involute and 20 degree stub. You see, in any gear we don't have only a single tooth, right? Or a very less amount of teeth. So there is a minimum number of teeth which we should ensure. For this 14.5, this is 32. For 20 degree full depth, this is 17, and for 20 degree stub, this is 14. Okay, that means we should ensure that this gear should have 32 minimum number of teeth. Okay, if its angle is 14.5 degree, this pressure angle is 14.5 degree. Okay, if we use this 14.5 degree full depth involute, then it should have a minimum number of 32 teeth. Okay, otherwise it will create interference. It may be more than 32, but minimum 32 it should have. For 20 degree full depth also it should have 17, minimum 17. For 20 degree stub it should have 14. Okay, in general in your question these two will be there. Okay, we will not use questions won't come from for 20 degree stub. Okay, next we'll talk about the force analysis, right? Force analysis I already told you that when two gears are meshing like this, okay, so this is the force that we apply, okay, and it has two components like this, right? So this is PR, this is PT. Okay, we neglect the effect of PR. Okay, the radial force. We have written this as PN also. PN, nominal force, tangential force, or radial force. These are same. Okay, PN or PR both have same. So we neglect the effect of this one and we consider PT. Okay, this one. Right. So we take that load as the static load in this case. Okay, PT, and later we modify this to a new load that is called P effective. We'll talk about that thing. Okay, by considering the effect of variations, we modify this PT to P effective. That I'll tell you later. Now, for the time being, we take this PT as the force which is causing the gears to rotate. I mean, this gear is pushing this gear with the force of PT. Okay, PT, and this is rotating in this manner. Okay. Now, how to find this P? We have actually found this. Okay. See, PT can be found using the torque 2mt by d. Okay. So d here is diameter dp or dg. If you are finding, if you are designing the pinion, then you will put dp here. If you are designing the gear, then you will put dg here. Okay, I'll tell you how to which one to design. Okay, how to design. Now mt, I told you that how to find this mt, 60 into 10 to the power 6 into power in kilowatt divided by 2 pi n. Okay, this is the formula, right? So find after an np here. If you are designing for pn, you put np, then you find nt, put it here, then you find out this force, okay, pt, which is static force, right? This is the force analysis, right, that we have spoken about. Next is, let's say, gear tooth failures, right? Gear tooth failures. Okay, so there are two type of failures. First one is breakdown, okay, or breakage of gear tooth. Next one is surface destruction. Alright, so breakage of gear tooth. Now see how to we'll visualize this. So this is a gear, right? You must understand when I write draw like this. This is the portion of the gear I have drawn. This is the complete gear. Okay, this is the center, and here we have another tooth. Okay, so this is the gear. Okay, this is how I have shown. Now see this gear. Let's say this gear is connected to a very heavy load, and this gear is very you can say weak, or the materials are not same, right? And this is trying to rotate this gear, but this is very hard to rotate this one. Then what will happen? There is a chance of breakage of this one. It will break here somewhere. Okay, break near to this edge. Now the gear tooth has broken, right? And this will not be operational. We have to replace this gear in this case. Okay, because even if one tooth breaks, we have to replace the entire gear. Okay, so that is a problem, and we should avoid the breakage of one tooth, right? So we'll now talk about this. We'll talk about this later on. Okay, surface destruction. Now let's talk about this one. Now you know that, you see, there should be a minimum amount of force, or you can say that see, suppose this gear has just started to push this gear, okay, with some force. Okay, let's say 10 Newton, right? 10 Newton. Now this is unable to rotate this gear, right? Okay, now increase the force to 50 Newton. Okay, still it is unable to rotate, right? So let's say at some force 100 Newton, okay, it can just, or it still is unable to rotate this force. But you see, the material has such a property that if you cross 100, let's make it 110, then this will break. Okay, that means you can say this gear tooth, if you apply more than 100 Newton force on this, okay, there will be reaction force. Since it is not rotating, equal and opposite reaction force will be there. So 100, if it crosses 100 Newton, then this gear tooth breaks. That means the maximum amount of force that we can apply is 100 Newton, right? So in your gear design, we term that is a strength. Okay, this is actually a force. Okay, previously we have termed the maximum value of stress as the strength, but here the force we termed as strength, and this particularly is written as beam strength. Okay, beam. Why it is a beam? So we'll talk about that now. So look at this. Now this is the gear tooth, right? Okay, fine. So you can see that this part, okay, is free and this part is fixed. Okay, this is fixed to the gear, right? So this is similar to a cantilever beam. Cantilever beam. Now see, cantilever beam looks like this. One side is fixed, one side is free, and there we apply the load. Okay, here also that load PT, okay, the tensile force is applied here. We assume that there are certain assumptions. We assume it is acting at the tip of the gear. Okay, so like that, linearly distributed. Now if we show you the isometric view of this, okay, then it will look like this. Okay, so this is the gear, and here the force PT is acting, or P. For the time being, we can write P or PT or whatever you want to write. Okay, so we just want to find out that maximum amount of P that can be applied, so that the gear the gear remains unbreakable. Okay, it doesn't break, right? So next thing here is, okay, let's take the dimensions. This is H, okay, this is T, the thickness, alright, and this is the face width, we call it. This is face width, this is thickness, this is some distance from the free end to the fixed end. This is the distance. Now we don't want, now the cantilever beam bends, right? So this also has a tendency to bend, and if it bends enough, then it will break. Okay, but we don't even allow it to bend, right? And I mean, we have to prevent the bending in this case, and it will fail due to bending. Okay, so that's why we consider the bending failure. So formula is mb into y bar by I. So using this formula, okay, there is a derivation, you can have a look at your book. So if we just take this as P, not PT, any force P, so P can be given as M B sigma B, okay, into this thing is T square 6 H, M has been multiplied, so M has been multiplied here also, so that they get cancelled out. So M is module here, okay, module. So this term here is actually written as capital Y, and which is known as Lewis form factor. Okay, Lewis form factor. Now you know how to calculate Lewis form factor, okay, from the data book. I'll come to that. Now see, this is the general formula. Okay, if we attain the maximum value of P, which is called the strength, okay, and in this case we write it as S for strength and B for beam, so beam strength. Okay, remember this is not a stress, maximum value of stress, rather this is a force, Newton. This is in Newton, okay, and this is in Newton per millimeter square. Okay, this is the maximum permissible bending moment, bending stress. So this sigma B here can be found using this formula SUT by 3. Okay, SUT is the ultimate tensile strength, okay, of the material, of the gear material. So this formula now we can write it as SB equals to MB sigma B into Y. So this is the formula for beam strength. Okay, so right, when you are asked to find out a beam strength, use this formula. Right, B is the face width. In general, B lies between 8 times module to 12 times module. Okay, and we take B as 10 times module. Okay, that means B by M ratio will be 10. Okay, normally this thing is given in the question, but if it is not given, you can assume it as B equal to 10 times module. That means if you put here 10 times modules, this is 10 into M, something like this. Okay, so this is beam strength. Alright, so similarly there is a formula for wear strength. Okay, I mean the second part, that surface destruction that we have spoken about, okay, is this. You see, when two gear tooth, okay, mashes with each other, when the two gears mashes with each other, see, if the gear they are operating very heavy load, and they can say sudden change in the load, okay, then their force is very high. We don't want them to slide over each other, and we don't want them to physically contact, so we put lubricants in between them, lubricants, okay, like we did in your bearings. Here also we put lubricants. Now due to heavy load, the lubricant film may break. I mean, lubricant film will squeeze out, okay, they will press each other so hard that the lubricant film will come out, okay, and the metal to metal contact takes place. Okay, that is one condition. Another one is if there is, although we design them for purely rolling over each other, but they may slide, okay, then also there will be some problem. While sliding, pitting will occur, surface pitting. That means waviness. Okay, so this is the thing in the gear tooth. Some waviness, surface roughness will occur. Okay, and due to metal to metal contact also, some roughness, the gear will wear off. Okay, so that's why we should again find out some value of force. Okay, if we apply beyond that force, there will be wear. So we call that maximum amount of force as wear strength. Okay, right. So we'll come to wear strength later on. Okay, but we'll now talk about beam strength. I'll just describe wear strength in the next video. So now we see. Okay, we have now learned about beam strength. Next thing is, okay, one important thing is, see, in your question it will be given design a pair of gear. Okay, there are two pair of gears matching with each other. This is the power and all these things will be given, right? So what you have to do, you first have to know which one to design. So there are two gears, pinion and gear. Okay, one of them will be smaller, one of them will be bigger. So pinion and gear. So out of which one to design? You see, you have to always design only one gear. Okay, not both of them together. Okay, so, and this is not the case that you always have to design pinion. You might have to design gear also. How to decide that thing? We'll look at that. Now see, if two conditions, if both gears, okay, that means pinion and gear both have same material, okay, and they are made of same material. Actually, you should write are made of same material. Then remember, then pinion is the weakest. Remember this. Okay, pinion is the weakest, right? So in this case, see, if both the materials are given in a question, that both have this material, 40 C8, 50 C8, whatever material will be given, then you straight away design the pinion. Okay, I mean, you do the calculations for pinion. Suppose you want to find out the MT, then 60 into 10 to the power 6 kilowatt 2 pi in place of N angular NT, because we are designing for pinion. So everywhere you write dP in place of D, ZP in place of Z. So everywhere you do it for pinion. Even you find out the module for pinion. Okay. So second condition is if both gears are made of different materials. Okay. Then what to do? In that case, then find this thing, sigma B into Y, capital Y. Okay, the last two terms of the beam strength formula. So sigma B, you know how to find out sigma B, right? So sigma B can be found by this formula. Okay, SUT by 3, and Y, you have to find out this for both the gears. Find this for both gears. Actually, you have to do it for both the gears, for both. Okay, that means sigma B into Y for pinion. Sigma B will be same. Oh, sorry, they will be different, because SUT for pinion, because they are different material. They are made of different material. So pinion ultimate tensile strength will be different, and gear ultimate tensile strength is also different. Okay, so this is for pinion. You do it for pinion, sigma B SUT by 3. Okay, ultimate tensile strength for the pinion divided by 3. Find out sigma B. Y, I mean, you need to know the number of teeth, okay, in pinion. Okay, from that, I mean, ZP will be given, or you have to somehow get the value. So using this, you have to get your Y value, that is Lewis form vector. You find out sigma B and Y, mean multiplied by Y. Okay, you find out. Then for gear also you calculate this sigma b equal to SUT for G, the gear, and Y for number of teeth. If you know for gear, then you calculate Y. Then you calculate sigma b into Y for the gear. Okay. Now, out of whichever is less, okay, whichever is less among these two, okay, this quantity, okay, sigma b into Y, whichever is less for, if it is less for pinion, if it is less for gear, then design that, okay, design that gear. I mean, if you find this as less for pinion, then you design the pinion. If you find this factor sigma b into Y is less for gear, compare these two, okay, then you find, then you have to design the gear. This is very important, okay, at the beginning you have to decide this, right? Okay, so I mean, you don't think that this will be always small for the pinion. It depends upon the material, okay. If SUT is more for pinion, then you may have to design the gear, okay. So check it. Or if your materials are same, then you don't have any problem. You can directly straight away design your that pinion, okay. So next thing is, we will next talk about next thing. We'll talk about something very important that I told you before. This effective load on gear tooth. Load on gear tooth, which is, we write this P effective. P is F. Okay. Now we have learned that in a gear tooth, right, there is PT, these forces acting, right? Okay. Now some things like service, okay. Now say, okay, let me start from the beginning. MT we find out using this formula, 60 into 10 to the power 6 into kilowatt divided by 2 pi n, right? This power here, okay, is the power you're supplied by the motor or the driving unit, okay, fine. This one kilowatt. Now but in practice, okay, both the gears, they are in machine, okay. So sometimes if we connect the output gear to some maybe let's think about the automobile, okay. So there will be acceleration, deceleration, okay, more load, heavy load, less load will be changing, okay. So load